Okay, so before the break, yeah, I have everything. We looked at the rotation, how to describe orientation or attitude of a rigid body in space. We came to the conclusion by a 3x3 rotation matrix, which we can parameterize by 3 parameters. Now, what 3 parameters are we going to use? And one way, and there are many ways, one way to parameterize this rotation matrix is by Euler angles. And of course by Euler angles, because the whole concept of orientation or rotation or rigid body is all, of course, invented by Euler. Yeah. Now, what are Euler angles? Euler angles, that is like a recipe. It's, I always say, like baking a cake. It's like baking a cake. Now, why do I say that? Because you just have to follow the rules in the right order. And if you do the wrong order, you don't get a cake. That's the thing. So, how does it work? Well, first align, so that's a 0 step. Align this B frame, the body fixed frame, with the inertial frame. So you just align the bodies. That's the idea. That's a 0 step. And then the first step is we're going to rotate. Rotate about the z-axis over an angle phi. So that's the first rotation. Then the second step is, again, we rotate. Now about the rotated x-axis over an angle theta, I guess, yeah. And then the last step is again a rotation. We're going to rotate about the rotated, meaning there have been 2 rotations already, z-axis over an angle psi. And I really want to stress out that this is a recipe. You have to do the steps in this order and not in another order. And another way of writing down these Euler angles is by saying we call this the ZXZ Euler angles. And sometimes it's also called precision, nutation, and spin. And that has to do with that initially they were looking at spinning objects where the large rotation was the last axis, the z-axis, and then it was tilting with respect to the z-axis and moving in the plane. But I don't like that naming. It's in the book, but I don't like it so much. It's only about heavy tops and so on. What's also clear is to say these are 3-1-3 Euler angles. That's also a nice way to identify them, because you just name the order in which you rotate about the axis. Now, if you read the recipe, you sort of understand what happens, but you immediately sit with your hands like this, right? And to try and understand what's going on. And, well, I always like to tell this story. Yeah, lecturing is about storytelling, right? So I spent a sabbatical year some 18 years or 16 years ago in the US at Cornell University, nice Ivy League university. And I spent there 1 year. And my contribution to Cornell University is 1 picture. Only 1 picture. But actually it's a beautiful picture. And I'm going to share this picture with you. So that's my 1 year work at Cornell. Well, let's start. It's quite a simple picture, actually. So we start with our inertial frame, right? And what does the recipe say? Align everything. So my body fixed frame is initially aligned here, and I'm going to rotate my body about the z-axis. So I have to give them names, x, y, and z. And the rotation I'm going to draw as a real physical rotation. And we call this a can. It's like a hinge where you really think, oh yeah, the rotation is about the z-axis, and these two different parts, they can rotate with respect to each other, and I know what the axis of rotation is. Now if you then look at the recipe, the second step is rotate about the x-axis. And it says the rotated x-axis. So here we have again a reference system, a coordinate system. And about this axis, this one, I'm now going to rotate over an angle theta. So again, why not draw this such a nice can? So this was the angle phi, and this is grounded, right? So this is really fixed to the ground. And this guy is theta. So this is phi and that's a theta. Now then the recipe said the third one is a rotation about the rotated z-axis. So that's again here, this vertical line. And then we draw again a can here. We put a symbol there for psi. And then here is where the body is. So here we can now write this x prime, y prime, and this z prime coordinate system. Now you would say, yeah, but that doesn't fit because all these points, all these center of rotations, they should be one point. It's all in one point. Well, that's true, but the beauty of the picture is this is like an exploded view, where by exploding the view, I explain how the mechanism works. So it's really a mechanism which you can build of three of these hinges in series. And of course, for the real mechanism, you have to make sure that these points all coincide. And you do that by making gimbals, which can rotate with respect to each other. Gimbals and gimbals and gimbals. That's then the trick. You make a virtual rotation point by having two rotation points at the end. But that's not the point here. The point is here that I have an exploded view of how Euler angles work. And Euler angles are just a mechanism. It's a machine. It's with your Legos or K'NEX or whatever construction stuff you have, you can build this. And then you can see how that works. And then finally, of course, in this here is my rigid body. So here things are moving. Let's move back again. 100. Where am I? 100. Where's my 100? Yeah. Oh. And here is my inertial frame. And by these three angles, I can keep track of the orientation. Now, in the beginning, I said it's a recipe. It's like baking a cake. So how do you bake a cake? Well, you take an oven and you put the oven on. It's quite important to start with that. And then you take a form and then you put that aside. You take some flour and you take some, what else do you need? Some butter and some sugar, and you just mix it all nicely together. Put it in the form, put the form in the oven. After 1 hour you get it out and you have a cake. Now imagine that you do it the other way around. So like you put the oven on, you throw all the stuff in the oven, you wait an hour and then you put it in the form. That doesn't work, right? Or you mix everything, put it in the form, put it in the oven, get it out and then light the oven. Also doesn't work. So there's a real order in all these steps, and that's the same with Euler angles. How do you find then the rotation matrix for these Euler angles? Well, you can find R by divide and conquer. Actually, it's a whole Napoleon approach. We're going to divide and conquer. How do we do it? We look at the three different rotations, and then we just combine those three different rotations in one rotation. So the first step in the rotation is a rotation about the z-axis, and we are already very familiar with that. So if we just draw a system where we have x-axis, y-axis, and here x with a triple prime because it's like some intermediate coordinate system, and here a y with some triple prime, and I have an angle phi here, then, well, of course I have here my z-axis and also my z triple prime because the z-axis is the one about which I'm rotating, so that doesn't change. And then I can, well, readily write down what my rotation matrix is for this one. Now, for all the matrices I'm now going to derive, I want to know what the body fixed stuff is in terms of the inertial. So I always have to think starting from this to this. So on the right hand side I have here x with a triple prime, y with a triple prime, and z with a triple prime, and the outcome is x, y, z, because the rotated body related to the fixed world. You can also turn it around, but for now I'm interested in this. Well, then you have to find those 9 entries, which are in this case only a function of one angle, phi. And it's sort of super simple because we already saw that the z-axis doesn't change. So meaning x has no effect on z, so that's a 0. Y has no effect on z, so that's a 0. And the z is just passed on. The z remains the z. So that was easy. And for the other two, the z prime has no effect on these, so this should also be zeros. So we already filled out how many numbers? 1, 2, 3, 4, 5. So 4 numbers to remain. Well, then we just have to look at the picture, and there are various ways to do that. In my head, what I usually do is I say, well, let's assume that we just have x prime as a unit vector. So we have this unit vector. What component do I get in the y, and what do I get in the x? Well, if this is a unit vector, then I get cosine phi in the x, so that's cosine phi, and I get a sine phi in the y, so I get a sine phi here. Now I make this as a unit vector. How many x do I get? Well, minus sine phi, this is a minus, and here again cosine phi. And by such I have built the rotation about the z-axis. Well, the next step is, of course, you do that for the x-axis, rotation about the x-axis. So again, we have a coordinate system here. Now the coordinate system is, of course, with our the one here. That's our sort of base system. And that base system, we are going to rotate about the x-axis. So x and then y to z. So apparently this is y and this is z, and the x is then here up. Is that right? No, that's not right. Then the x is apparently down. Is that true? X, no, still not true. It was correct initially, was it? Yeah, it was correct. So x to y is z. Yep. So it is up. So that was good. So this system, but it's the intermediate one. It's with the triple prime, and then I go back to a double prime. So this is again double prime, y with a double prime, and this is a z with a double prime. And the angle here, theta. That was the second rotation. About the x-axis, so with a triple or the x with a double, doesn't matter, they're identical. Same matrix, I can write x, y, z, vectors x, y, z. Then I want to know what the double primes are in terms of these triple ones. 1, 2, 3, 1, 2, 3, 1, 2, 3. Let's give this a name, by the way. Let's call it r phi. Now, in this case, the rotation is about the x-axis, so that's simple. 1, 0, 0, and again zeros here. We've seen it in the z-axis. And then again, take a unit vector. Take, for instance, the y double prime as a unit vector. And then what do I get? I get here a cosine phi, a cosine theta, sine theta, minus sine theta, cosine theta. So this we call r theta. Now, last step is again, that's again a rotation about the z-axis. It was z, x, z. So z, x, z. So now we still have these coordinate systems with the x and the y, only which x and y are these? These are the double primes, right? And then here is the body frame with the single primes. Z with the single primes, and here I have my z single prime, z double prime. They are identical because that's a rotation. Well, I needn't have to think actually for this, because I can copy the result from above here. Only the primes are a bit different. So I have x, y, z here. I have x, y, z here. The entries is now the angle we're going to use. Oh, it should be a signed angle. There's a direction. Is psi. So this is a cosine psi, minus sine psi, sine psi. And again, the axis of rotation is the z. And I'm going to name this one r psi. So we see now that we have these three compositions are the compositions from this triple prime thing, to this, that's in this coordinate system, then here I have also a coordinate system with the double primes, and then here I have a coordinate system with a single prime. So I go from no to triple, double, single. This chain of events. Then this chain of events is also written down here. So let's write it like these results in a matrix vector form. So we have apparently x is r phi of x with the triples. Then x with the triples is again r theta with the x of the doubles, and the x of the doubles is apparently the r phi with the x of the single prime. I forgot the single primes here, of course. Now then, you see you can substitute all the stuff in each other to finally get the composed relation that x equals r phi times r theta times r psi times x prime. Or in other words, this gives our rotation matrix as a function of these three angles. So, and what do we see? We see that it's a product of three matrices. And clearly, if you look at this, now you know that in matrix calculation, if we have matrix multiplication, if we have two matrices, A times B, how do I say times like this? That is usually not equal to B times A, right? In our matrix calculation world. If you have matrix A, matrix B, multiply them, then that's not identical to matrix B times A. Or in other words, if you do r phi, r theta, r psi, that is not identical to, let's change the first for instance. Or in other words, the order matters. The order in which you do your steps. So the order in which you bake your cake is important to get a successful cake. The order in which you use the Euler angles matters to get successful Euler angles. Now, meaning that Euler angles are not vectors. Euler angles, and you would tempted to say something like this: V is phi, theta, psi, are no vectors. No. No. No, they are not. And why do I say that? Well, if you have two sets of Euler angles, V1 and V2, then if you first do V1 and then V2, that is not the same as V2 plus V1. Order does matter. Sorry? For Euler angles. For Euler angles, you cannot say. And let's be specific. Let's take a specific example. So let's look at a specific case. So let's take our head and our nose. And here we have ears, and here we have eyes. Right? Then our coordinate system for now is such that our x is pointing forward, our z is really eyes. Our z is up, and our y is this is left. This is left. Yeah. So forward is x, left up. So this is a nice coordinate system. And now I want to do Euler x z x z rotation, and I have two sets of Euler angles. And let's take a very simple set for the Euler for the V1. I take the first one as minus 90 degrees. We think it should be radians, of course, normally, and the V2 is just a very simple Euler rotation. There's only one rotation. That's a 90 degrees here, and the other ones are 0. And now the question is, of course, what happens when you do V1, first V1 and then V2, or you say, no, I do first V2 and then I do V1. Do I get the identical results? Yeah? Well, why not? I mean, people say, oh, Euler angles, they're like vectors, we can add them. So, and if you can add them, if you think you can add them, then the commutative law must they are, vectors are commutative. V1 plus V2 is equal to V2 plus V1. And I want to get into your head that that's for Euler angles not the case. And so we have to do an experiment, and I need you for that experiment. And I have to do something. So it is clear what the assignment is, right? We know our coordinate system now. Yeah, and I have to put the camera there. You see. Yeah, we see sort of the audience. I need to see half the audience. That sort of works. Yeah, sound goes a little bit out. It is dangerous to walk with my sound thing, so I'm going to break it probably. If I do like this, I hopefully won't forget. Okay. I'm going to divide you in two. So you are group 2 and you are group 1. And to do the experiment, it's best to just stand up, because sitting you cannot do like this and this and this and all those kind of things. So, okay, group 2 just listened. I'm going to start with group 1 and then I'll come back to you. So I propose to now we cannot read. Where's my thing? Air server. Yeah. I propose that so group 1 is going to do on the left V1 plus V2, and group 2 is going to do V2 plus V1. Now, it is so hard, rotations. I always forget. So, this is X, this is Y, and this is Z. And if we look at the two rotations, the first is a set of Euler angles tells you apparently about your Z-axis. Well, that's clear, right? And a minus 90 degrees. So, let me try and rehearse now. Plus is like this. So, this is minus 90 degrees about my Z, right? That's doable. Okay, don't do it yet. And then the second one, V2, is about your x-axis, that's your nose thing. And then it's plus 90. So like this, right? I mean, how difficult can it be? Okay, so group 1, let's try. So first V1. What was V1? Yeah. In the yes, okay. And now about your rotated x-axis, 90 degrees. Yeah, okay. Hold it like that. Don't move. Perfect. Now we start with you. So plus 90 degrees about your nose axis. It's like this. And now about your z-axis, which is this one, minus 90. So plus would be this. So my guess is something like this, right? Are we both orientated the same way? And can I hear something? Are we? No. Okay. So thank you for assisting me in this experiment, and I think that this class, 28 people today, will never forget that Euler angles are no vectors, period. So Euler angles are within a special realm. And why is that important? Well, because we cannot do all these vector additions, and they're just parameters. They're numbers to parameterize a rotation matrix. Period. That's it. Okay, having had the orientation now, so the orientation of a body we do with rotation matrix, which we parameterize with 3 parameters. These Euler angles, A. But if we look at our Euler equation, we have sum of the torques is mass moment of inertia, angular speed plus angular acceleration times angular speed, mass moment of inertia times this guy. Now we have to find the relation, of course, between time derivatives of these guys and these omegas. So we have to know phi dot and theta dot and psi and maybe also the angles themselves, phi, theta and psi. And there's apparently some relation with omega. Already if you look at the mechanism, you're rotating about axis, so these are sort of like rotational speeds and then like rotational vectors, and then if you combine them then, but we have to be aware, or the angles in itself are not vectors, so angular velocities are vectors, so there you see the discrepancy between the two. So we have to go to step back to our basic thing, and our basic thing is we have a rigid body, and within that rigid body we have this coordinate system, and we have within that body a point P donated by a vector P. We have nice coordinates, x prime, y prime, z prime, and we have a reference system x, y and z. This is no x. Now how do we find the position of a point? We say, well, x of p is the x of c plus p relative to c. And as I said today, for now we're going to forget this translation. It's not so important. I only want to look at this part, which is in my picture now is this p, this point p. Okay. So the general formula now tells me xp is this xc plus xp with respect to c. How do we write this one? Well, we're used to not using the body, the inertial coordinates, but we used to write these invariant coordinates in the body, because these are constant, constant numbers. But if we do that, we need the rotation matrix in front, because we need to rotate them back to the inertial frame. Or in other words, what we are doing is P in the fixed world is this R times this P prime. Okay, now let's look at the velocity of everything. So the velocity of point P is the velocity of point C plus the relative velocity of P with respect to C. Or in other words, with our R x prime P C, we have to take the derivative of this guy, and that is of course r dot times this guy plus r times the time derivative of x prime p of c. But since these numbers are constant, this thing is 0, right? So the only part we now have for our rotational speed is this part. So this is about rotational speed. But there is one problem. If we look at our expression, this is in the inertial frame and this is in the body fixed frame. And I actually want to relate everything, so I want to know my speed in my body fixed frame, which is, I have this part, x prime pc, so this is a dot. The only thing, I have two different coordinate systems, and I want to have everything in one coordinate system. Well, that's easily done, because for my x prime pc, of course, I can write my r transpose times the one in the inertial frame. So finally I get, for my relative speed, I get r dot r transpose times xpc. Or in a shorthand notation, my p dot is now equal to r dot r transpose times p. And this is our velocity relation. Now, unfortunately, when I look at this, I do not see any angular velocities yet. I see a complex thing. I see r dot and r transpose, and I actually have no clue how to proceed. Well, yeah, I can take the partial derivative of r with respect to the angle, and then the angle with respect to time, and then multiply everything. But then it's becoming a complete chaos, I think, and I have no clue what's going on. So let's step back and let's think a little bit about this mapping. So what is RT R transpose? Well, I have seen, before the coffee, I saw a mapping which looked a lot like this. Remember the constraints? R times R transpose is the identities. Now, if I differentiate that with respect to time, what do I get? I get R dot R transpose plus R dot transpose is 0. Oh, I always like when things are 0. That makes it simple. And if we really take a close look, then these resemble each other a lot, right? Because the R dot R transpose in the transpose is equal to R times R dot transpose, right? So if we take the transpose of this one, then that's identical to this guy. So let's say we have a matrix W, which is R dot R transpose. Then apparently this statement tells me that W plus W transpose is 0. Or in other terms, W equals minus W transpose. Now, W is a 3 by 3 matrix, so W is something like this. 3 by 3 entries. Now, which matrix is for a general asymmetric matrix? What do we have on the diagonal? Well, if you have a 1 on the diagonal, then in the transpose we also have a 1. And can 1 be minus 1? It's not possible, huh? There's only one number where the negative is identical to the positive. And that number is 0. Okay, so on the diagonal we have all zeros for this matrix. Now, if we have a number A here, we have minus A here, and we have a B here, minus B, and C, minus C, right? So apparently for such an asymmetric matrix, we only have 3 unique entries. Yeah? And I'm going to write the W a little bit different with the 3 entries. I'm going to write it like this, with the 3 zeros, and then I'm going to write A, B, C, and then here's minus A, minus C, and here minus B. Now, any idea why I write this in such a quirky, strange plus-minus form? No, it's a bit strange. Well, let's continue. Let's take this matrix, 0, 0, 0, with those strange A, B, C, minus A, minus B, minus C. You see, I make it on purpose asymmetric, and multiply it with the vector x, y, z. Then the outcome of this matrix vector product is, what is it? Minus C times Y plus B times Z, C times X minus A times Z, minus B times X plus A times Y. Do we recognize this? Yeah, cross product, exactly. So that's the A, B, C cross product with the X, Y, Z. So this asymmetric matrix is a way to write a cross product. And now I'm going to introduce a vector, which I call omega, and they have 3 components, omega X, too quick, omega Y, and omega Z. And I'm going to write this omega in this matrix form as a for the cross product. So we have 0, 0, 0. I have omega, omega X, omega Y, omega Z, minus omega X, minus omega Y, minus omega Z. It's all legitimate. I have 3 parameters. I call them omega X, omega Y, omega Z. And accordingly, together with that vector goes this matrix. We call it the tilde. We call it omega tilde matrix. It's a way to write a cross product as a matrix vector product, because this whole cross operation is strange. I mean, it's a strange way. We find it always hard to manipulate that. Now we have to step back to our result. Remember, we had r dot r transpose, and that was this 3-parameter thing, which I now just define as this omega thing. And by such, I have defined that the velocity of this point P is equal to omega cross P, or with this omega tilde times the vector P. And now, yeah.
There is no way to represent that matrix in terms of the identity of the other vector. Like I could divide the omega tilde as I cross something or something like that. Not cross.
Yeah, with no, with the alternating tensor epsilon I j k. That's true, but I'm not going to do that here. Because we're in the end we use usually MATLAB for our calculation. In MATLAB you have the thing called cross, but you also can make the matrix, and you have matrix vectors. And I want to work with that for now to make things clear. So going back to our initial thing, we had our P dot equals our R dot R transpose times this P. So apparently this R dot R transpose is this omega thing, as I said, or in other words, let me write it out. It's a 0, it's a 0, it's a 0. It's omega x, omega y, omega z with, and these off-diagonal terms, minus omega z. So here I have actually the whole relation between my angular speeds and my Euler angles and their time derivatives. The only thing I have to do is I have to expand this now. So R dot R transpose equals, well, R is the rotation matrix is a function of my Euler angle, so I first have to take the derivative to the first angle times that times R transpose plus the second angle, theta dot R transpose, plus the last angle, psi dot R transpose. And that is apparently equal to, yeah, now the copy and paste should easily work. So that's apparently equal to this guy. So by just expanding this, and that's just hard labor, right? Because in itself, the rotation matrix is of course the product of these three. So it's a nice cosine and sine thing, and I'm not gonna write it out because it's too many sines and cosines and everything. And of course you can substitute that here because now you see the dependency on the various angles, but you see there are a lot of R, phi, psi, transpose and whatever, which you have to multiply. And so I always say this is hard labor, and it's really hard labor because you are doing double trouble. If you have to do this in a regular way, and then you end up with one expression for omega x and also one for minus omega x. Well, that's nice, then you can check your work. And you also get 3 zeros. Oh, that's also nice, you can check if you really get zeros. So you have a feeling, I'm really doing too much here. There should be an easier way. Now, if you do something by an easier way, we always call that, that is a bend in the road. No, I had a nice thing for that. How do I call that? The easy way, or the insightful way is, yeah, what do I don't remember how I called that. But that's always dangerous. If you say, well, there's an easy route to do it. That's a dangerous bend, we always call it. Dangerous bend. A bend in the road, dangerous bend. Now, what is the easy way? Then we go back again to our figure. And our figure is these My only contribution of 1 year hard work at Cornell University. It's not completely true. I also worked a little bit on bicycle dynamics and control, but really, so these are the 3 hinges in series, right? And here we have our body, our final body at the end, and this is our inertial frame, this is our body frame, and then, well, you can put X, Y, Z with that, that's okay. But let's put the angles with it. So this was the angle phi, this was the angle theta, and this was psi. Now, if you think in rotations, you can draw in the picture this arrow, this vector, and you can say this vector is omega phi. Because you know what the direction is, and you know what the magnitude is. Because the magnitude of this thing is phi dot. Right? Super clear. We know the magnitude, we know the direction, it's a vector, this is it. The same I can say for this one. So I can write a vector here, omega theta. We know the direction, we know the magnitude, theta dot. And the latter one, the last one, is again this one, psi dot. We have the vector in this direction and we have the magnitude. So you could say for the omega of the body, I just add those 3 vectors. I take omega phi plus omega theta plus omega psi. And if I do that, I get my omega vector. Now, what are these omegas? Well, I know this guy, I know it in this reference frame. I can express it in this reference frame. Well, let's not write it there. I know what it is in this reference frame, because there's nothing about the x, there's only about the y, and nothing about y, only about the z-axis. So it's 0, 0, phi dot. Yep. Now the next one, so this guy. Well, in this local reference frame, I know what it is. It's about the x-axis. So it's a vector with a theta dot and then 2 zeros. But I want to have everything in relation to my inertial frame. So I have to do some transformation to get here. And which transformation is there? Of course, there's also this r phi. Yeah? I have to transform it because that first hinge rotates this second coordinate system in which the theta is. And likewise, for the last one, I can write 0, 0, and it's about the z-axis, right? The last one. But now we have 2 rotations in play. So first we have the rotation of this theta, the theta axis. And then we are back in this system, and then we have this r phi. If you then expand this, that will be really easy, because the result there will be omega x, omega y, omega z is equal to, and then we say phi dot, theta dot, psi dot. Now it is really easy, but I don't know it by head, of course. So I have to write, look at my notes, 0, 0, 1. It's a cosine phi, this is a sine phi, and this is a 0. This is a sine phi times sine theta, yes, I agree. This is a minus cosine phi times sine theta, yeah. And this is a cosine theta. And this is everything actually we need, because it gives us a nice relation between our omega in our inertial frame, a matrix A times, yeah, now I'm tempted to write this. The time derivative of the Euler angles. But note, it's not a vector. Eh? These are just algebraic numbers. Eh? So where this vector A is phi theta psi. But from the experiment, you know, no, they're not vectors. But I can write them as algebraic components, as a column vector. Now here we have this relation of omega versus the Euler angles. Of course we want to have the inverse relation, because the state is determined by the angular velocities, and we want to know what are the time derivatives. So we have to do A dot is A minus 1 times this omega in the n frame. Now, to determine a minus 1, that's something with 1 over the determinant of a times and then some entries of this guy, right? That's usually the way it goes. Now, what is the determinant of this A matrix? Does anybody... This determinant is important because if it would be 0 at some instant, then we even cannot find the inverse relation. So we cannot determine what the time derivatives are of the Euler angles. Now, actually, it looks complex to do the determinant, but it is sort of easy because we have 2 zeros here. So the determinant is this 1 times the subdeterminant of this guy over 2 by 2. And a 2 by 2 I can do out in my head, right? So that's this one. So that's minus cosine phi squared. So minus cosine phi squared times sine theta. And then minus this one, and that's minus sine phi squared sine theta. So that's sine theta. So the inverse of the matrix is 1 over sine theta times a number of entries. 1, 2, 3, 4, 5, 6, 7, 9 entries. When is this singular? When can we not find the inverse? When theta is 0. So singular when theta is 0 plus or minus k pi, right? So that is actually, we are in trouble because we cannot find the expression for the time derivative of the Euler angles in terms of Euler angles and angular speeds. This singular configuration can easily be understood if you look at the mechanism. So if this is the mechanism with the 3 hinges, then this is the configuration approximately. This is the initial one. This is the one where theta is 0. And in this case we see that all these 3 hinges are in the same plane. Or in other words, all these angular velocities, so this was the phi dot, this was the theta dot, this was the psi dot, these are all in the, what is it, x, y, in the xz plane. In the xz plane we have omegas, and out of that plane we are not able to describe an omega about the y-axis. So the thing we call this usually Gimbal Lock, and that's a famous thing in Euler angles, that there's always a singular configuration. Gimbal Lock, that's horrible because you cannot describe the speeds and you cannot change easily the configuration. If you build the mechanism, you will also see that if you put it in this position, you're not able to do any rotation about the y-axis because it is stuck, the mechanism. Now there are ways to circumvent that. Is you just redefine all your angles. In the middle one you add 90 degrees and you say, hey, this is my new description, my new set of Euler angles, and then I continue my calculation. A major disadvantage of that is, of course, if you have discontinuous variables, your whole numerical analysis of numerical integration with accuracy, estimation of error, the whole thing is gone, down the drain. So if you want to do it right, if you reformulate your angles, you have to stop your numerical integration, reformulate your problem, and start it again. And then maybe you are within error bounds which you initially want. Anyway, this is something we don't want, and there are ways to solve that, but we need to have a new topic, and that's for next week. See you all next week.